lesson 7 is an introductory lesson to the beams. Like statics is all about, or mainly about the beams. Besides the beams, we also talk about the other things like the Bohr's notation at the end of the day, right? We discuss about centroids, stuff like that. But anyway, right now I want us to appreciate the knowledge of calculating the reaction forces at supports, right? That is today's lesson. We're just going to be focusing on, I'm just going to be showing you how you are supposed to calculate the reaction forces. And like I said on the concept breakdown, you need to make sure you master the difference between a simply supported beam and a cantilever, and the concentrated point load versus uniformly distributed loads. You need to know the difference, as well as static equilibrium conditions, those ones where we're saying the sum of the upward forces is equal to the sum of the downward forces. Sum of the moments in an anti-clockwise direction are equal to the sum of the moments in the clockwise direction. So here I was just pasting some different kinds of beams. We have what you call a simply supported beam. You can see it with this horizontal item is what you call the beam, this thing, and it will be having the supports at its ends, or maybe in between. It can be at the ends, it can be in the middle, not really in the middle, yeah, in between, along its length, but it will be having the supports, 2 of them. In this case I put RA and RB at the ends. One can be maybe slightly, this RA can slightly move to somewhere here, and RB as well, or anything, as long as you're having 2 supports. That is a simply supported beam. The other one that we have is a cantilever, and it looks like this. It will be having a fixed end and a very, very free end on the other side. So usually in the exams you'd find it like this in the diagrams. So we're saying it is fixed firmly at one end, and the other one, it's just free, it does whatever the hell it wants. So here's the thing: when you're looking at a cantilever, the single fixed support, it actually carries the entire load, right? The entire load is actually carried by the side A in this case. So when you're calculating the reaction, you're just doing it. It's the sum of all the downwards forces combined, right? Then we also have this situation. Types of loading profiles. So we can have what you call the concentrated point load. This is basically what N2 was all about. You're having a force that is pointing like look at F, maybe force F like that, right? That's a concentrated. Then we also have something called uniformly distributed loads. If you happen to be if you have been to N3, you might remember these, but if not, it's fine, okay? These things are going to discuss them right now again, because your exam is also concerned about that. So you will be having load that is actually spreading all the way. It can be maybe somewhere, but along the entire length of the beam, and it is usually in newtons per meter or kilonewtons per meter. And the thing is, before you perform any other calculations, please you must convert the UDL, okay, the uniformly distributed load, to the point load, right, by multiplying by whatever, if it is in kilonewtons per meter, and you see that all the other point loads that you're dealing with are in kilonewtons, you just multiply by the length of the beam, then you will be fine. Then the other thing, it's very important, you have to make sure that it is in the middle, right at the center, okay, so that yeah, that is basically what we then do, because it was uniformly distributed. When it's point, you place it at the center. All right, here's the other thing. If you notice, N2, we used to talk about the light beams, where you don't really consider the mass. Here, we're very much concerned about the mass. So we also treat it the very same way with the very same way the way you treat the uniformly distributed load. Alright, then the other thing, again, don't forget to convert the mass to newtons. That is, if it is not given in newtons, by multiplying by 9.8 most of the time. Sometimes, of course, you check the instructions there on the question paper, or maybe if they didn't really say, just appreciate 9.8. It is only in mechanotechnics where we discuss where we perform mechanotechnics, fluid mechanics, we really use 9.81.
Okay.
Then after that, appreciate the total weight at the force at the center, and that on it will be pointing. Usually you make it point downwards, right, from the center. So that was the thing. That is the introduction today. So these examples are nice. I mean, they are good for an introduction, and so are the activities here. So we're having a situation here. We're having a uniform beam with a mass of 100 kilograms, and the length is 7 meters, and it is simply supported at the ends A and B. And then it carries 3 concentrated point loads. The 80 Newton, which is 2 meters from the left end. It's sort of this. There it is. It is supported A and B. Then we're having 80 newtons, which is 3 meters. So something like this. Let's call it 3 meters. 3 meters, 80 newtons. 2 meters rather, from the left end. The other one, 120. So if you add another 2 here, it makes them 4 meters, which is 120 newtons. And from the left again, and 60 newton, 1 meter from the right end. So here from the right end we have 1 meter, and the entire item, the length is 7 meters here. This is 2, that is 4, that is 5, so this is also like 2 meters. Alright, so this is what we have. Then they wanted us to calculate the reactions at forces A and B. This is basically, most of the times, this is what your N2 is like, right? So it's cool. I'm just taking you from the baseline. All right, so this is it. And what do we do next? What we do is that we have, unfortunately, the mass, which is 100 kilograms. So now, boom, we need that. Before we do anything, make sure that you convert your mass to that. And like I said, the mass, it will be treated like a UDL. So in this case, it is 3.5 meters from A. So let's call it this one, right? So this is where it is. So W is equal to mg. In this case, it is 981 newtons. All right, so that is the case, and this is 3.5. Cool. Then the next thing, we can then appreciate sum of the clockwise moments is equal to the sum of the anti-clockwise moments. Now the thing is, you can just clockwise, clockwise, it's basically, this is how the clock goes, right? So you are looking at the arrow that will make the beam go like that, right? So if you look at this arrow that let's say A, right? If you push A, the beam will definitely. So we have A. So we have reaction at A. However, here I called it B, but it's fine. What is B? B is with A on the left, right? At its left, and we have A on the right, and okay, it's cool. So it's cool. So if you look at this, if you look at A can push this item in that direction, and then this is what happens, right, to the beam. And then let's suppose you make the 80 Newton force move. What is going to happen is that you would see the beam moving in this direction, something like that. So those are the things that we are, so they are moving in the opposite directions. So the anti-clockwise moments that we're talking about, and the clockwise, so that is clockwise and that is anti-clockwise. So let's look at the forces which are going to make the beam move in an anti-clockwise, because that is the thing that I started off with there. So if you look at A is not going to make the item move in that anti-clockwise direction, because that is not where the arrow is literally pointing. It's B, and B is 7 meters away from A. So usually when we are taking the moments about A, you are calculating B. Okay, so that's the thing. When you're taking the moments about A, you are calculating B. When you're taking the moments about B, you're calculating A. Okay, that is the thing. So if you look at S of B, is going to be 7 meters away from A. So that makes it RB times 7. The other one which can make which is pointing in that direction, if you can see that, it is basically we were talking about what? The anti-clockwise, right? Anti-clockwise. Which is the other one there? That is gonna make the item go in that direction. We cannot see anything else, like honestly, there is nothing else that is gonna be like that. We are considering the moments about A. So boom, we're done on this side. Then let's see the forces which are going to make our beam take the clockwise direction. So clockwise now in this direction. So we're talking about the forces that are kind of pointing downwards, So we're talking about that one. Wow, what was that? After 120, it was 60. We're talking about 60, we're talking about 120, we're talking about 80, we're talking about 98, 981 there. So we can take the 80. How far is it from A? It is 2 meters away from A. Remember, we are considering these with respect to A. Then the other one that you're seeing, maybe if you like, you can just move on to the next one. 981 how far is it? It's 3.5 from A. So that is the thing there. My bad. It was supposed to be 3.5. So let me put a comma here. 3.5 and then 120. How far is it from A? It's 2 plus 2, that is 4. So 120 times 4, right? That's what we did. If you look at the other one, it's 60. How far is it from A? It's 2 plus 2, that makes it 6. So we're going to say 60 times 6, and then boom, you just do the things, you add everything you want, and you find the value of RB. Then you take the moments about B. This time around, like I said, if you're talking about B, you are finding A. If you're talking about A, you're finding B, right? So let me just pull back my drawings. Let's hope they're gonna come back. Yes, nice one. All right, so this time around, now we're looking at the moments about B. So we are calculating A. So how far is A from B? Well, it's 7 meters. So RA times 7. And after that, we need to look and see, do we have anything else that is gonna that is pointing in the same direction as A besides B? Of course not, right? So that's the point. Then we're done. We move on and look at the clockwise. Well, we have starting closer to B, maybe, we have 60, which is 1 meter away from B. Remember, now we're respecting B. Then we have 3.5. 3.5. I don't know where my comma was really going. It's like it was. Where was my comma going? 3.5 away from B as well, and 120 is 2 plus 1, that makes it 3, and 80 is 2 plus 2, that is 4 plus 1, that makes it 5. So then we multiply by 5. Nothing else really. Then you add and do the things, and finally you get your answer. Well, that is how you can do that, but here's the thing. You can verify by using the equilibrium test. It's a nice approach of doing all the mechanics at both items in this case, so that when you perform the verification, you can literally get reassured that, you know what, I really did the right thing. Besides that, I would say, you see here you got RB, and this is what we had our A here, our RA, and with our RB. Then we had 80 newtons. We also had what? 120 newtons. Something else?
60.
And 60. There were only these ones, right?
Yes.
So, after getting your RB here, you might not want to go through the mechanics here. That is the other way. So you can say, we're saying what? Sum of upward forces is equal to the downward forces. So So the upwards, the ones that are pointing upwards, with RA plus RB. The ones which are pointing downwards, it's 80 plus 120 plus 60. And we have, so RA will be equal to 80 plus 120 plus 60. I'm just let me just plug out real quick. It's 80 plus 120 plus 60. This gives us 260 if I'm not mistaken. Then we subtract RB, which we calculated 600 and what, 33.357. So if I didn't make a mistake, 633 point what? What did you get? Oh, well, yeah. Why is it not balancing? Because something is wrong. Something that is missing was the mass, right? 981 as well. Was it 81? What was the mass? 981.
The mass was 100 kg.
The weight?
Yeah, it was
981, right?
What?
So we're supposed to we're supposed to say plus 981 there. Then after that, I don't know what you get if you say that. If you add that, it's 1,241, right? 1,241 there, and then you subtract the item that you got, which was what? 633.357. So this gives us, so RA is equal to 607.643, right? Which is basically what you'd have. So like I was saying, you know, you might want to do it like this. It's cool if you check the next question doesn't require you to do the checkings, you might just do it like that. Okay, that's nice. All right, so that was it here. And the other example, we're having a uniform beam with the mass of 120 kilograms, and that is 80 meters long, and it carries a UDR of 150 newtons per meter. Then after that, it is over its left half. It is supported at its two ends, and you need to calculate the direction forces at the supports. So, well, boom, this is what we have. It is supported at the ends, so we have RA here and RB over there, and they said it is 8 meters long, and 4 meters down the line we have the uniformly distributed load, right? Which is 150 newtons per meter here. So which actually transfers to what? The beam is going to end up with 2 meters. Along the 2 meters, we will have, because they said it's first left half, right? Half of 8 is 4. So we got that, and if you look at that, we are looking at 150. If you multiply by 4, what do you get? you get 600. So this is 600 newtons right in the middle. Then what else do we have? That's it.
Yeah, that's that. We
Great.
calculated the way back.
Okay, then the mass is 120 kilograms. If you convert 120, I'm just gonna be using 9.81 here. It gives us 1177.2 newtons. So in the middle of, so this was 2, and this entire thing is 8, so 4. After the other 2, this is where we have 1177.2 newtons, and there is our RB over there. There is our RA. Okay, that being said and done, we need to then determine the sum of the clockwise moments is equivalent to the sum of the anti-clockwise moments, you know. So, well, so that is the thing. So anti-clockwise, which item is going against the direction? Oh, things are just happening. Alright, so we're saying in that direction we only have RA and nothing else, right? So RA is, how far is it from RB? 7. Then clockwise, the item that is pushing the item down, we have 600 newtons as well as 1777.2. So how far is 600 from RB? This is 2, that is 4, so that makes it 6, right? So we multiply 600 by 6, and then 1177.2 is 4 meters away. Then we do the things and perform the calculations and find. Then you can go on and test the equilibrium. Since they are always in equilibrium, you are supposed to get the things right. They should balance. Alright, so that is the thing. So I'm just gonna show you the questions on activities here, and you're going to try and answer those questions, and then you can also check the solutions that I provided there, and you will be fine. Do you have any burning questions?
No
questions?
No questions. With this.
Great. So that's it. See you in the next lesson.
Yes.